Today I will be explaining the binary system. The binary system is a system that uses two digits, 1 and 0. The topics that will be covered today are converting into binary, the ones complement method, the twos complement method, the sign and magnitude method, and the binary coded decimal method. Converting a number to binary number. How to convert to binary. Since the binary system consists of two digits, then each column is worth twice the one before. Hence, it is placed/raised to the power of 2. To convert to binary, you must use the products of the multiplication. So the numbers in blue. So let's say you want to convert the number 2 into binary. Then you place a 1 on the column which has the number 2, and all the rest turn to zeros, because 2 is the only one you need. If a number is greater than 128, don't fret. You can add other columns by using the rule that each column is worth twice the one before. If you don't understand as of yet, do not fret. In the other slide, we will be practicing some more examples. For these practices, we will only use 6 bits. Note that bits are just the amount of columns you use. So this is one column, this is the second column, the third column, the fourth column, the fifth column, and the sixth column. In order to get the binary number, you must find the number on the table. If you don't find the number, then you can find two or more numbers that add up to that number. And if you find those numbers, then you place a 1 under the numbers you will use and a 0 under the ones you will not use. So enough of information, and then we'll get right into the practice. So in this practice, we'll be finding the number 10 and converting it into binary number. So here in the table, we can see that there is no actual 10 in the number, but we can see that there are two numbers that add up to 10, and these two numbers are 8 and 2. So 8 plus 2 equals 10, and since these are the only numbers you need, then you will place a 1 underneath them. All the rest of the numbers that you do not need will turn into zeros. Therefore, we can conclude that the number 10 has the binary number or code of 001010. The second number that we will be converting is 16. So, as I explained earlier, we will be using 6 bits. And the reason for this is because we have 6 columns. So first, we look at the table and see if there is a 16 in it. And here, unlike the previous example with the 10, there is a 16 in there. So we don't have to plus any other 2 or more numbers to get that number 16. Therefore, the only number we need from this table is 16. So we place a 1 underneath it. And then, according to the rules, all the other numbers that we do not need will turn into zeros. Therefore, we can now conclude that the number 16 has the binary code or number of 010000. For the third and final number, we will be using 45, which is a larger number as compared to the others. Again, we will use 6 bits. So firstly, we will look at the table and see if there's any 45 in it. And here we can clearly see that there is no 45. Therefore, we will need to find 2 or more numbers that add up to 45 in order to complete our table. Here we can see that the number 32 is the closest to 45. Therefore, we can add other numbers to the 32 to get closer to 45 and to get 45. So here, if we add 32 and 8, we will get 40, which is not enough. So then if we add 4 to this already makes a 40, we will get 44. Therefore, we only need one more number, and that one more number will be a 1, which is here, to complete the 45. So, since we only need the 32, the 8, the 4, and the 1, we place ones underneath them. And for the ones we do not need, which are the 16 and 2, we place zeros. Therefore, we can conclude that the number 45 has a code, binary code to be exact, of 101101. So to recap, in these examples we learned that the binary code or number for 10 is 0, 0, 1, 0, 1, 0. We also learned that the binary code for or number for 16 is 0, 1, 0, 0, 0, 0. We finally learned that the binary number for 45 is 1, 0, 1, 1, 0, 1. This then are all the examples we use to learn how to convert regular numbers or decimal numbers or whole numbers into binary numbers. To add binary numbers, we should remember 4 simple rules. Number 1, 0 plus 0 equals 0 without 0 carry. 0 plus 1 equals 1 with a 0 carry. 1 plus 0 equals 1 without 0 carry. And lastly, 1 plus 1 equals 0 with a 1 carry. To add binary numbers, we should remember 4 simple rules. The first rule is that 0 plus 0 is 0. The second and third rules are that 0 plus 1 is 1. 1 plus 0 is 1. And lastly, 1 plus 1 is 0 with a 1 carry, which will give you 10. Now, using the 4 rules, we will solve the problem 1 plus 1 plus 1. The rule that applies here is the fourth rule. Now, knowing that 1 plus 1 will give you a 0 with a 1 carry, we know now that since we have the 1 over here, all we'll have to do is plus this 1 with the supposed 0 that was supposed to be here, which is here. So now when we plus this 1 and the 0, we'll get 11 because we'll bring down this 1. Now, to re-explain, using this rule, we know that 1 plus 1 will give you a 0 with a 1 carry. But since now we have an extra 1, we will plus the 1 with the 0, which will give us a 1. And now all we have to do is bring down the 1 carry, which will give us a 1. Therefore, the answer will be 1, 1, or 11. Now, using the 4 rules, we will solve another example. The example we have here uses 4 bits. 1, 2, 3, and 4. So we have 1, 0, 1, 0, plus 0, 0, 1, 0. Okay, so we know that 0 plus 0 will give us a 0. We know that 1 plus 1 will give us a 0 with a 1 carry. Now we know that 1 plus 0 will give us a 1. And lastly, we know that 1 plus 0 will give us another 1. Therefore, the answer to this problem is 1, 1, 0, 0. Now, in regular numbers, using the table, we could say that 1, 0, 1, 0 is 10, because 8 plus 2 will give you 10. And we can say that the 1 over here is in accordance with the 2. Therefore, we have that the second binary number is a 2 as a regular number. And now if we plus this, the regular number for this binary number would have been 12. Now this would be all for the addition of binary numbers. One's complement. One's complement is basically the inversion of binary numbers. And since we know binary numbers are only 2 digits, then the 0 will turn into a 1 and the 1 will turn into a 0. So whenever you have a binary number and you want to convert it into one's complement, all the zeros you have will turn into ones and all the ones you have will turn into zeros. Below we have an example, and it is 1, 0, 1, and then the ones complement to that specific binary number will be 0, 1, 0, because you have converted all the zeros into ones and all the ones into zeros. The previous numbers we turned into binary are the same numbers we're now going to turn into ones complement. Remember that ones complement is the inversion of binary numbers. So enough talking and let's start. So if it's the inversion, this 0 will now become a 1. This other 0 will also become a 1. And now this 1 will become a 0. The other 0 will become another 1. And this 1 will become a 0. This 0 will become a 1. And this is now the ones complement of 10. So all we did here was do the opposite of the binary. So if the binary number contained a 0, then the opposite of a 0 would be a 1, since there's only 2 digits in the binary system. This is basically how we got 1, 1, 0, 1, 0, 1 as the number 10's ones complement. All we did was do the opposite of what we have for the binary number. Now we'll turn the binary number of 16, which is 0, 1, 0, 0, 0, 0, into ones complement. We will use the same method we used for the previous example, and all we need to do is invert the numbers we have here. So if we invert a 0, it will become a 1. And if we invert this 1, it will become a 0. All the other zeros we have here will all turn into a 1, because that is the inversion of the zeros. So 1, 1, 1, 1. Again, all we did was do the opposite of the numbers. And since the binary system only has 2 digits, which are either 1 or 0, then if we have a 0, we'll invert it to a 1, and if we have a 1, we'll invert it to a 0. The last example we have here is 45. So now we'll turn the binary number, which is 1011101, into 1's complement. So again, as previously mentioned, all we'll do is invert the numbers. So then 1 is inverted into 0, 0 is inverted into 1, 1 is inverted into 0, the other one is inverted into 0, this 0 is now inverted into 1, and this last one is inverted into 0. Again, all we did was invert. So if there is a 1 here, we'll invert it into a 0, and if there's a 0 here, we'll do the opposite and invert it into 1. Remember, the rule for 1's complement is basically to invert all the numbers. 2's complement. For the quick method of the 2's complement, one must start from the right side of the number and write everything normally if a 1 isn't encountered. Once the 1 is encountered, you keep the 1 and everything from the left side of the 1 will flip/invert. So the 2's complement method is to find the first 1 coming from the right side to the left side and flipping everything from the left side of the first 1 and keeping everything, including the 1, from the right side. As you can see in the example, this is what is done in the second number you see there. So for the regular binary number, we have 0, 1, 0, 1, 0. Now converting it to the 2's complement, we have 0, 1, and that is the one that was just mentioned is the first one. So everything after this one will flip/invert. So now it will be 0, 1, 1, 0, 1. Using 6 bits, we'll be solving for the 2's complement of the binary number 1, 0, 1, 1, 0, 1. The rules state that we should start from the right side, and the first one we encounter will be the one we keep. And here we can see that the first one is the first digit we see, so we keep. Everything else after this one will be flipped. Therefore, we'll have 1, we'll flip the 0 and it will be converted into a 1. This one will be converted into a 0. This other one will be converted into a 0. This 0 will be converted into a 1. And this 1 will be converted into a 0. Therefore, the 2's complement for the binary number 1, 0, 1, 1, 0, 1 is 0, 1, 0, 0, 1, 1. We'll do the same procedure we did in the example previously shown. So, first, starting from the right side, we'll see if there's any 1s. But no, the first digit on the right side is a 0, so we continue. Now we stop at the first 1. Therefore, everything from this side will remain the same, and everything from the left side of the first 1 will change. So we keep the 0 and the first 1, and then everything else will flip. So this 0 will turn into a 1, this 1 will turn into a 0, and these 2 zeros will turn into 2 1s. Therefore, the 2's complement for the binary number 0, 0, 1, 0, 1, 0 is 1, 1, 0, 1, 1, 0. For the last example, we will repeat the same procedure as we have been repeating. So, starting from the right side, we see if we have any ones, and unfortunately we have a 0. We continue and we have another 0. We continue and we have another 0. We continue and then we have another 0. And once we continue again, we see that we have the first one. So everything from this part, the right side of the 1 will remain the same, and everything from this side will flip. So everything from this side will remain the same, including the 1, and the only thing that will flip in this binary number will be the 0, which will become a 1. So we can conclude that the 2's complement for the binary number 0, 1, 0, 0, 0, 0 is 1, 1, 0, 0, 0, 0. Sign and magnitude. In sign and magnitude, 0 represents positive and 1 represents negative. The leftmost number of the binary number is the sign, since according to whether that number is positive or negative, then that number alone will change. All other numbers are the magnitude and will stay the same. To find the sign and magnitude of a binary number, we must first remember that in sign and magnitude, 0 represents positive and 1 represents negative. We must also remember that the number at the leftmost side is the sign and all the other numbers are the magnitude. So, looking at the sign that we have here, we have a 1, and the 1 is represented by a negative. And in this problem or example, we are looking for negative 40. Therefore, this number will remain the same because 1 represents negative. Therefore, negative 40 would be 1, 0, 1, 0, 0, 0 in sign and magnitude. Following the same procedure we did in the previous example, we look at the leftmost side, which is the 1. Here we are looking for a positive 35, and following the rules we can see that positive is represented by a 0. So the leftmost side digit has to change to a 0. Therefore, it would be 0, 0, 0, 0, 1, 1. Again, the reason for the change is because 0 represents positive, and here we are finding a positive number. In this example, we are now looking for a negative 35. So, looking at the leftmost hand side, we see that a 1 is a digit. Looking back at our rules, we see that a 1 represents a negative. Therefore, this binary number will stay the same. So, the sign and magnitude of the number negative 35 will be 1, 0, 0, 0, 1, 1. Again, it is because of the rules. The rules state that positive is represented by a 0 and negative is represented by a 1. Binary coded decimal. In binary coded decimal, we have 1010 representing positive numbers and 1011 representing negative numbers. So basically, we need to find the binary sequence for each number and then add them together. The number/binary in front of that number is concluding using the positive or negative codes. For example, 328. You will find the binary number for all numbers in 328. And since it is positive, the number in front, when they are all brought together, would be 1010. Now, for the binary coded decimal, we must remember that positive is represented by 1010 and negative is represented by 1011. We must also remember that the BCD uses 9 digits, 9 decimal digits to be exact. Now then, the example states, what is the BCD representation of negative 328? Now, knowing the rules, we know that BCD requires us to separate all of the digits. Therefore, we will find the binary code for number 3 on its own, number 2 on its own, and number 8 on its own. Because the binary coded decimal method only requires 9 digits, the binary codes for all 9 digits are already provided, and they use 4 bits. Here on this side, you can see that we have all digits of this number, negative 328, all alone here. So what we're going to do is we're going to fill in all of them in the equal space, and then we're going to put them together to form the code. Therefore, knowing our rules, we know that the negative sign is represented by 1, 0, 1, 1. Thanks to the binary codes already being provided here, we won't have to go through all the trouble of finding them. Therefore, all we have to do is enter the codes. So for 3, we have 0, 0, 1, 1. For 2, we have 0, 0, 1, 0. For 8, we have 1, 0, 0, 0. Now then, according to the rules, we know that the negative sign should go first. Therefore, we will write 1, 0, 1, 1 first, and then we'll follow them up by all the other digits. Therefore, we will continue with 0, 0, 1, 1, 0, 0, 1, 0, and 1, 0, 0, 0. This code over here is now the BCD code for negative 328. This example is essentially the same as the previous one, just that the signs are different. So now we're looking for positive signs. Now then, let's enter the numbers. So for positive, we'll have the binary number of 1, 0, 1, 0, as that's the representation for positive. Next, all the numbers here, 3, 2, and 8, will be the same as the previous example, just that the only thing that will change now is the sign. So for 3, we will have 0, 0, 1, 1. For number 2, we'll have 0, 0, 1, 0. And lastly, for number 8, we'll have 1, 0, 0, 0. Now that we have the binary numbers, we can begin to formulate the code. As we know, the first thing that has to come here is the sign. So now we'll put 1, 0, 1, 0, and then we'll follow it along with the other numbers. So then it will continue with 0, 0, 1, 1, 0, 0, 1, 0, and lastly 1, 0, 0, 0. Therefore, the binary code will be 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0. That will be all for my presentation. Thank you for listening.